All right, so let's try this. If we've looked at a cantilever beam with a point load, let's look at a simple supported beam with a distributed load. Now, before we get started, let's just write down some things that we know. Do we know, just based upon support conditions, do we know anything about the displacement? Yeah. Where do we know the displacement? We know the displacement in A, right? So I could come over here and I could say, hey, my displacement at x equals 0 should be 0. What else? Any other place we know the displacement? The displacement at x equal L is also 0.
What about L? What would be the maximum?
Well, for this particular problem, you can probably infer that it will bend uniformly and that at half L the slope will be 0. But that's only true for this case. If I change that load in any way, that's no longer true. These are always true. So let's stick with the ones that were guaranteed. Okay? So those are going to be my two conditions that I'll use. The first thing I need to do is write the moment equation for this. So to help me out, I'm going to assume that I have a reaction at A and a reaction at B. And also to help out with my calculation, I'm going to replace the distributed load with a concentrated equivalent. So what's the area under the loading curve? Well, it's a rectangle, so it's going to be base times height. So I'll have a equivalent load of WL. And where's the centroid for that? Right in the middle, half the distance. So that's L over 2, depending on what side you want to work from. So what I'm going to do now is I'm going to find these reactions. Let's go ahead and think ahead. I'm going to eventually cut this structure and look at it at some distance x to find my moment. So in that strategy, you want to work the left side or the right side?
Left side.
I think the left side will be easier. So really all I need is the reaction at A right now. So to get my reaction at A, I'm going to sum moments at B. So let me come over here and sum moments at B and make sure it's in equilibrium. So about B, my concentrated equivalent load creates what kind of moment? Positive or negative? Positive. So I've got a load of WL times a moment arm of L over 2. And then I've got my reaction creating negative moment with a moment arm of L. So you can see my reaction at A is WL over 2. Shouldn't be a surprising result. Basically half the load to A, and I bet if we sum forces in the Y direction, we find the other half the load is over here at B. So now I'm going to draw my free body diagram for this little chunk of the beam at a distance x. I know my reaction here is WL over 2. I have the distributed load, which you'll remember has an intensity of W. So what is the concentrated equivalent for that piece? It's still a rectangle, so base times height, which will be x times W. So this will be WX. And the distance from the cut to the centroid? Half the distance, or x minus 2. And then, of course, at the cut, I would have positive shear. And right now, we're not worried about shear. We're only concerned right now with moment. So there's my free body diagram for that. To find the moment, I'll just sum moments at the cut. So again, I'll use right-hand rule for my sign convention, and I'll sum moments at our cut to make sure it's in equilibrium. So starting here on the left, this moment would be positive. How about the moment Wx? Is that creating positive moment about the cut or negative moment? Positive. So I have a force of Wx times a moment arm of x over 2. And then I have this load, my reaction load, WL over 2. What kind of moment does that create? Negative. So I have a force of WL over 2 times a moment arm of x. So let's solve for the moment. So my moment as a function of x should be, let's see, to be minus Wx squared over 2 plus WLx over 2. Well, does it work? Do I know something about the moment in my beam? Do I know what's the moment at A? So that means the moment at x equals 0 should be 0. Does my moment equation give me that? 0, 0. Yes, it does. Do I know the moment somewhere else? How about at B? What's the moment at B? 0. So that says that at x equal L, the moment should be 0. If you put in L here, what do you get? You get 0. So that works. So that is my moment equation. And again, for the first part of the class, you're done. But now we're not done. What do we do next? We need to solve for the slope. So we know that the slope is equal to the integral of the moment divided by EI integrated along the length. So let's do that. So what is the moment? Well, our moment equation over here looks like it's got a W and a 2 as a constant. I can factor that out. And we're going to assume my EI is constant. So I'm going to end up with W over 2EI as a common factor. And then I'll have the integral of minus x squared plus XL. Did I do that right? Looks okay to me. Again, this is a polynomial, so this shouldn't be hard to integrate. So again, I'll have my W over 2EI, bless you. And what do I get here? I'll get minus x cubed over 3, that's the integral of minus x squared, plus x squared L over 2, plus an integration constant. Now at this point, if I know something about slope, I could use that to evaluate C1. So, we've already talked about this, but we already know that probably at L over 2, the slope is 0. Probably. And it is true. But I would encourage you not to try to predict that. I would encourage you to use the things that you know, which are 2 displacements. And since I have conditions in 2 displacements, I can't evaluate the slope with that. So I just have to leave C1 alone and integrate it again. So the displacement is the integral of slope. So let's integrate that. So again, we'll have the same constant. So the integral of this will be minus x to the 4th divided by 12 plus x cubed L over 6 plus C1 integrated is C1x plus a second constant C2. So all I have to do now is evaluate C1 and C2 to match these displacement conditions. Usually the one with x equals 0 is the best one to start with, so we'll do that. So I'll first start here that, hey, I know the displacement when x is equal to 0 has to be 0. So I'm going to plug in x equal to 0. 0, 0, 0. All I'm left with is C2. So what does C2 have to be equal to? 0. I also know that at x equal L, the displacement has to be 0. So I've got to plug in x equal L here. So I put in x equal L here and L here. You can see these are both L to the 4th. So I've got 1/12 plus a 6, which is what? A 12th, right? So that should be W over 2EI. And then this term evaluated at L over, at x equal L is L over 4 divided by 6, right?
I mean negative.
Well, this is negative 1/12 and this is positive 2/12, right? A 6th is 2/12,
Oh.
right?
Yeah.
So you should get positive a 12th. I wrote 6. I meant a 12th. I don't know how I can wiggle that in there. I'll put it in right there. Can you see that? Sorry about that. I messed up. And then evaluate C1 at L. So I just have to solve for C1. So C1 will be equal to minus WL cubed over 24EI. So I divide it by L, that's how I get L cubed. And then, of course, the 2 times 12 is 24. And all I have to do is plug that back into there, and I have my displacement equation. So now I know and also I can plug it in here, and I have my slope equation. You guys like that? I sense that you don't. No.
When we do these, can our answers just have E and I as variables, or do we?
Right,
have
so that's a good question. So what this tells you is that the only way E and I can come out of the integral is if they are constant. If they're not constant, they would have to stay in the integral. Right now, most of our problems, E will be the constant because we usually deal with one material, steel, concrete. And as long as the cross-section stays the same, then the I will be constant. But you can see this. What does this tell you? As your material gets stronger and stronger, which means E goes up, what happens to displacement? It goes down. As the moment of inertia gets bigger and bigger and bigger and bigger, what happens to displacement? It goes down. So I becomes the biggest thing that you as a designer can choose to minimize displacement. That's why when you take steel design, if you choose to, the steel table is just full of all the standard steel shapes, and it gives you this data for the steel shapes. So when you say, oh, I need one that has a certain moment of inertia, you go to the table and you see all the ones that are available to you. Probably the one that weighs the less, which means it costs less, would be the better choice. There'll be a lot of ones in there that have that or a higher value, but you probably want to be efficient. Now, just to compare this to what's in the book, I'm going to plug C1 back into here and try to generate the equation for you. And I'll just do the displacement equation. So what happens now is my Y equation becomes this. You'll notice that if I plug this in here, what do I have? I still got W over EI as a constant. So I think I'll just start with that first. So the first term, that 2 runs in there and makes that 24. So I get x to the 4th over 24. The second term becomes x cubed L over 12. And then now I can plug this guy in. The W comes out, and I've got x L cubed x over 24. You guys see that? You'll notice that the numerator all have the same term. So that's really linked to the fourth, that's linked to the fourth, and that's linked to the fourth. So the terms all have the same order in terms of their units. X is linked, L is linked. Now you'll see that they've got really a common denominator there. In fact, I'm going to pull the 24 out now. And I'll get W over 24 EI. And what am I left with? Minus x to the fourth plus 2x cubed L minus L cubed x. So there's my equation for displacement. So you'll see a lot of times they like to do that. They like to pull these denominators out to this common term and then adjust it this way. So let's check real quick and see what the book happens to have. So if I slide in our book, you can see we've worked this problem. If you look over here on the right, you'll see the same result, except they pulled the minus sign out in front. So all the signs in here are changed, but that's because the minus sign is out. What's that? Oh, they pulled the x out too here. We have x to the fourth, we have x cubed, and we have x. They just pulled it out. I don't know why. I guess it's just style. So you can see our term, we have pretty much the same result. Super cool, huh? So any questions about this one? All right.